Hi, my name is Pavan, and today the topic I've chosen for the Breakthrough Challenge is optimization. And rather than try to explain it like any conventional textbook or video, I thought I'd give you a pretty interesting exploration or a type of journey in which we can apply this concept to something that students really enjoy so that students of all ages can understand this topic really much better and understand its true potential. So this optimization uh, concept or video that I'll be talking about will require you to know some basic differentiation, or it would be better if you knew some basic differentiation, as in what the definition is of differentiation. That could be found even through maybe watching some Khan Academy videos to learn like I did, the limit definition, which is pretty the fundamental aspect of differentiation. But for all purposes here, we'll think of differentiation as something that tells us the instantaneous slope, which means the slope at any point. So for example, what I've set up here is an equation, y equals ax squared plus bx plus c, and this is the graph of it. So now, what I've said is, when you take the derivative, and this is the conventional notation of taking the derivative dy with respect to x, it basically means that once we get this equation, if we put in any x value, right, any x value, whatever this gives us will be the slope at that corresponding x value. For example, if I take the tangent here, it should give me the slope for this x value. Now, if I put this x value, whatever x1, let's call it x1, if I put x1 here and I put the value, this expression will give me the slope at this exact point. Now, why is this useful? It's useful because we need to use this to apply it to optimization. And optimization is basically, by the mathematical definition, taking the best value out of a set of values, given values. And in this case, in most cases, it's either a maximum or minimum value, right? And in this case, you can probably see that it's pretty clear that we want a minimum value here, that we can actually find a minimum value, which can actually we can put a number on it. So what do? We realize here that if we take this, let's say we take the slope here, and let's take the slope here, the slopes basically change from negative to positive, and the slopes become smaller negative numbers as we go closer and closer here, and smaller positive numbers, until one point where the slope actually becomes zero, because to go from negative to positive, or positive to negative, the slope must be at zero at one point. So if we look at this tangent here, we can tell, as most of you must know, that if you have a horizontal line, the slope is zero. So we say, and since this tells us the instantaneous slope, the slope at this x value should be zero, which means we equate 2ax plus b to zero. And then we can find, because a and b are constants, we can find the value for x, and then we can substitute the value for x back into this equation, to get the corresponding value of y. So there we can find the minimum point. So that's the basic intuition and concept that you need to learn, you need to know before we delve into this exploration. So let's get to the actual exploration. And since I love football, so when I learned optimization, the first thing I thought of is whether optimization can be used in sports. And what I found out is pretty interesting, and I hope you guys find it interesting as well. As you probably all know, there's something called a free kick in football or soccer. And this free kick is when, let's say I'm somewhere over here, right? And this is the goal, right? This is our goal over here. And I have the ball here, and I want to kick it over the defensive wall. So we're looking at it from a side view. And I need to get it over the wall and such that it gets into the goal in the best possible position, which would probably be the highest position, right? So it can be out of the reach of the goalkeeper. Now, you probably understand that the initial angle at which you kick it and the initial velocity at which you kick it will affect how the ball travels. Because the faster you kick it, and the angle at which you kick it will affect it. So I've come up with a simplified equation, right? But for all purposes here, for this concept, we can just assume that this equation works. And this equation basically tells us, just to clarify, the y is the number of goals. So if we take a sample of a host of different initial velocities and thetas, and we try to see how many goals we can get with that same a number of repeated different experiments. So this is all experiments. Since it's a real world application, it's actually pretty interesting. I've actually gone to the football field using softwares like the tracker software. You can actually tell at what velocity and initial angle you kick the ball. And then you can use softwares to try and model an mathematical equation out of this. So now we want to use the same concept that we just learned from above of how we can optimize this. Because if we look at it, let's take a graph here, right? If this is my y and this is my x, I mean, this is basically, x is going to be something to do with velocity and theta. So we have v and theta. Now, if I have something where, let's say, we get a maximum point here, I'd obviously want to find this maximum point because this maximizes the number of goals. So we need to find the velocity and theta for which it's a maximum. And what do we do? What did we learn from before? We learned that to find that, we have to take the derivative and equate it to 0. But the really advanced thing that comes over here is the fact that we have two independent variables. So if we have two independent variables, we get something really interesting. This is where we get to a very advanced concept that usually students only learn in college, which is partial derivatives. So now that we have two variables, we need to take two derivatives. So the first one is that we have to take the derivative with respect to v naught, and the second one we have to take the derivative with respect to theta. So how this works is that for the first one, you have to take it with respect to v naught, but assuming that theta is a constant, which means, okay, so let's take the first part. We need to take the derivative of sine v naught plus 20, which is, I've given this table here, so you can take a look at this. So what this reduces to is cos of v naught plus 20. That's what it reduces to. And then for the other one, we do the same thing as doing it with respect to theta, assuming that v naught is constant. The reason why we don't have to consider this for this one is because then this whole thing would be constant, and the derivative of a constant is always 0. But it would reduce to sine of 20 minus theta. Now, just as we did learn earlier, now we have to equate the derivatives to 0. So cos of v naught plus 20 equals 0. And from this table, for those of you who haven't done trigonometry, you should understand that cos of 90 is 0. So all we can do is equate v naught plus 20 to 0. Now the reason we're only taking acute angles in obviously 90 is because we need to limit our domain, and in this case range as well. So because we need to limit the range because we need to restrict it to the application, which is that we need to know values which are only humanly possible, right? People can only kick so hard or at such an angle. So we get v naught is equal to 70, and we'll assume that it's given in meters per second. So we found v naught. Now what's our next step? We have to equate this to 0, which gives us sine 20 minus theta is equal to 0, which gives us, from this we can see that 20 minus theta is equal to 0, theta is equal to 20, we'll assume it's in degrees. So there you have it, we found it. Theta is 20 degrees, initial velocity is 70 meters per second, so that's what I need to kick the ball at to get a perfect free kick. So in this area, so what's a perfect free kick? In a more mathematical sense, optimized free kick. So basically I found a way to improve myself in football through simple math, and that's pretty amazing, at least for me, and I hope you guys found it interesting as well. So what we need to do now, as hopefully some of you have realized, is confirm whether it's a maximum, because we know that the slope is 0, but as seen earlier, the slope would be 0 for a minimum as well. And the best way to do this is use something called a second derivative test. But in this, and due to lack of time, I won't be able to explain everything about it. But I encourage you to research about this because this is very important, both in partial derivatives and regular derivatives. But in this case, it actually works out pretty nicely. You just have to substitute it back into this. So if we substitute v naught is equal to 70, we get sine 90 plus cos of 0. And sine 90 is 1. cos 0 is 1, so we get 2. And we know that this is a maximum because the maximum of the respective of sine theta is 1 and the maximum of cos theta is 1. This is from trigonometry. So there we found it. I hope you guys liked the video.